Okay, I'm at CEDIA 2023 and we're at the Trinov Ascendo Mad VR display, and it's my pleasure to chat with Geoffrey Heinzel. How are you, Geoffrey?
Andrew, how are you?
I'm very, very well.
Hope you had a good trip over.
I did, thank you. I'm looking forward to
Good
going
show
home.
so far?
It's been a long show.
Yeah, it has been.
I really wanted to talk to you about Ascendo. Ascendo's
Right.
one of those rising stars in this industry, I think. But Ascendo's doing things very differently. One of the things I've noticed about Ascendo is your choice to have your equipment tested and measured, but not just by yourselves, by a third party.
Correct.
So tell me a bit about the product. Tell me why you've chosen to go that path, and let's talk about the importance of that.
Well, I think let's talk maybe not first about our product, but
Sure.
why we went this path.
Yeah.
Also to do basically a third-party verification of our developments, let's put it this way. Because you can alter data. Even clipple measurements can be altered, And so we even publish the company that does the third-party measurements for us, and so they can be individually contacted, from our customers. And we do that because we also want to verify our data and our finding, It's not necessarily that two labs come up with the very identical data, So probably if we send the speaker to a third lab, the data would be slightly different again, But it's close enough to predict really a good room design. That's exactly why we, of course, show the data the way we do, because we don't only show the CEA 2034, which is basically the spinorama, which is the on and off axis, the reflected, the directivity, whatnot. But we also, on top of that, even though nobody asked us to do so, show the CEA 2010 or newer AS75 data, which is the compression data, shows you basically the power handling, where the speaker starts to compress, what's the distortion at what level of load of the speaker, because each speaker has pretty much the same behavior. When you approach, let's say, the higher level of the performance of the speaker, the bottom end of the frequency range of a loudspeaker starts to distort quite heavily, right? And so it's basically pick your poison as a designer, how much distortion, or for the customer, how much distortion you would accept in that system. And so without knowing that data, without having that data for each, let's say, third octave band down to the lowest frequency you want to run the speaker, how do you really design that system, right? Or based on RP22 standards, have a level 1, 2, 3, or 4 system, right?
I was about to mention, because obviously RP22 has just been released.
Right.
And, for those of you unaware, this is the recommended practice that CEDIA's put out on the design of a room, and
Correct.
It states certain requirements. And the question now to industry is, well, if you're designing a room, how do you know you're meeting those requirements if you don't have the data? So I think that what you're doing is going to cause the industry to have to lift, and it seems like at the moment you're leading the forefront there.
Well, yeah, I mean, for a room design lives off of a lot of different things, right? So first you place a speaker in a room, and you need to, of course, dial it in from an angle that you have an even coverage on your listening area, of course, or the coverage area, basically. But it's much more than that, because the speaker also interacts with the room, right? And so the room interaction for, let's say, wall bounds or wall reflections, floor and ceiling reflections is very important, because the way humans perceive sound is much more through the reflected sound than for a direct sound, right? So if the reflected sound sounds very different from the direct sound, there is something churning in your brain.
There's a dissonance in it,
and it adds to the listening fatigue. So speakers that have, let's say, an odd behavior, let's say in one or the other area, and when the reflected sound basically reflects this behavior, then something's odd, and your brain tries to correct for it. So you get a lot of listening fatigue. But with a speaker, let's say we design a point source coaxial, you have axiperiodic horizontal and vertical dispersion. So the reflected sound sounds the same as the direct sound.
And so you don't have that.
The brain doesn't need to work as much.
Yes.
And also, of course, the impulse response, the timing is very important for our brain, because we lived with speakers for 10,000 years, without speakers for 10,000 years. Now just we reproduce the sounds, right? And so a speaker should kind of be as authentic to a timing as the original sound is, right? And so when you originate a sound, that comes from a single point, not from 2 points. When I do that, you hear it, it's different timing. So, and they interact, right? And they interact at certain frequencies where the speakers are crossed over. And most speakers are crossed over at very sensitive, let's say 1 to 3K, right? Or even below sometimes when you have a three-way system, maybe at 500 hertz or 400 hertz. Also very sensitive, because it's right in where the human voice is, right? And so we're very sensitive when we're talking about home theater to the voices. And so you get these anomalies from direct sound and reflected sound, right? And that's why we feature point source coaxial loudspeakers, because there you don't have that kind of odd behavior, right? Because the timing and the frequency response is good.
Yeah. We have a lot of conversations with people about the difference between music speakers and movie speakers.
Yes.
Now, my position on this has been that's not a thing. What the goal should be is accurate reproduction of sound. And I'm curious, for your feedback on that.
Well, if you're familiar with the work of Floyd Toole and people alike, there's other people that blow the same horn, kind of, and me too, of course. There is good measurement data, and if a speaker measures well, it sounds well in a blind test.
Yes.
Right? So, enough said, I think.
Okay,
right?
Fair enough. All right. So the other thing that Ascendo's really getting a name for are subwoofers. Talk to me a little bit about subwoofers. We had a brief conversation yesterday, and one of the things I struggled with was the idea of a large subwoofer being fast. And you set me straight on that. I'm wondering if you could explain to people, because a lot of people might look at a subwoofer like this and it's a bit hard to understand. So take me on a quick journey through your subwoofer development and products.
There is a few systems in play here. One is the driver alone, right?
Yep.
Then, of course, there is another system which is basically the enclosure.
Yep.
So these systems, they come together as one and they interact. And so when you want to reproduce very low or ultra low frequencies, obviously you need a very large enclosure, because only with a very large enclosure the resonance is low enough to reproduce these low frequencies. Without that, with a small enclosure, you always have a fairly high resonance, because when you look at Hofmann's iron law, when you want to reproduce 20 hertz, you need just a monstrous enclosure, or even go below, even bigger, right? So that's why, for example, when we sell an 80-inch subwoofer or a 50-inch subwoofer, we recommend sometimes enclosure sizes of up to or more than 20 cubic meters. That's a room.
That's a decent subwoofer.
That's a room, right?
Yeah.
So, but why is that? Because we want to reach a very low resonance frequency of the woofer in the room, right? Let's say the 80-inch in such an enclosure reaches probably a system resonance frequency of about 10 hertz, right? With a system resonance of 10 hertz, my group delay curve or rise starts very low. So normally when I have, let's say, an 18-inch woofer in such an enclosure, right, for example, there my group delay rise starts at probably already 80 to 100 hertz. Starts rising, right? So the group delay at 30 hertz is maybe, I don't know, 20 milliseconds. Now, when I have a big woofer in a big enclosure, the group delay starts rising at maybe 30 hertz. So my group delay rises, but at 30 hertz, I still have maybe about 2 or 3 milliseconds. So it's 10 times faster, the big woofer than a small woofer, right?
Yep.
The second thing is, of course, is the force factor, the acceleration.
Yep.
So I'm using the same relation of force factor in a small woofer and a big woofer. Here I have a 21-inch voice coil. That's the voice coil of our 80-inch woofer. So the size and the force factor, just to give you a number here, the BL, that's the force factor of a motor. The BL of this 80-inch is 150. A normal BL of a very, very good woofer, let's say an 18-inch like that,
Yep.
that's about 25 to 30.
BL, yeah.
Yeah. So it's much higher force factor. So I mean, I can literally lift a car with that.
I think the other statistic that's really interesting is we talked about, you know, people not really understanding some of the voltage and current that's being applied.
Right.
And, you know, one of the numbers that came out recently was that there is voltage and current being applied that is similar or higher than three-phase to a home.
Correct.
Yeah.
I mean, we power test our loudspeakers, and for example, here the 32 has been tested with the currently most powerful amplifier on this planet, which is a 20 kilowatt mono amplifier that can put out a voltage swing of 460 volts.
Yeah.
You cannot blow up the speaker with this amplifier. So you cannot even power compress the speaker with this amplifier. So that means this speaker would handle more than the most powerful amplifier on this planet can output.
Yeah.
Yeah. So that just puts it in perspective. I mean, this subwoofer here, for example, we Klippel tested, and it outputs over 140 dB SPL at 30 hertz. Right? That's immense, you know.
So that's another question that springs to mind. You know, we've been looking at subwoofers and measuring quite a few, and you look at some of the ported subwoofers and some of the sealed subwoofers, and one of the things you see is you look at a subwoofer that is potentially very good, but it might roll off earlier, whereas you look at some subwoofers that are marketed as going very low, but in fact when you put them in the room...
But that's not realistic. I mean, yes, it is in a way, but only with the DSP applied.
Yep.
But when you now do a power test of this subwoofer, it becomes very non-linear very early, because you can only support that literally boost in the bottom end, which maybe seems to sometimes be 18 or 25 decibel, because each woofer rolls off, each woofer, you know, and the woofer is not different. The woofer speaker, let's say, package is not different.
Yes.
What makes it different is the DSP applied. But then when you apply, let's say 18 dB of boost, what is 10 dB? 10 dB is 10 times the power.
Yes.
20 dB is almost 100 times the power.
Yep.
So let's assume you have an amplifier of a kilowatt, right? We believe it's a strong amplifier. Now, so that means when you boost this subwoofer 20 dB to make it linear, and that's what you need to do actually in a small subwoofer, right? That means at 10 watts at the higher frequencies, let's say 100 hertz, the subwoofer is already at maximum power, a kilowatt, at 20 hertz. So the subwoofer runs out of steam, right? So what they do then, they apply a trick. Yeah, it measures at low power, linear, but then when you apply basically more SPL to the subwoofer or more input, then it becomes non-linear, right? Because you cannot overcome physics. You know, the subwoofer cannot travel 10, 20, 50 centimeters to really have the same output at 20 hertz as at 100 hertz, right? And this is the kind of data we honestly communicate with the market. Our subwoofer may look as it only goes to 30 or 40 hertz. No, it doesn't, because we just show the data without the DSP applied.
And it behaves differently in the room once it's set up and established and properly configured. So
yes, correct.
Yep. All right. Look, thanks very much. I really appreciate your time. It's been lovely talking with you.
Big pleasure.
And you've been very patient with us.
Thank you.
So thank
Absolutely.
you.
No worries.
We'll see you later. Bye-bye.
Thank you. Bye.